Okay, so welcome everybody to the next seminar in the data linkage and anonymisation series. I understand the streaming is working, so welcome today to Grigorios Loukides, who's going to talk to us about sanitization for sequential data. And just to mention that Robin might have circulated an email saying that if you'd like to email me at c.j.skinner@lse.ac.uk by the end of the seminar with any questions you'd like to be posed, I'll try and pass them on. So over to you, Grigorios, and perhaps to mention as well that you're soon to be at King's College London. Okay.
Thank you. Thank you for the nice introduction and for organizing the excellent program. I'll talk a little bit about sanitizing sequential data, and I'll start by giving you the setting. So here we talk about data which are sequential. By that I mean that the order of the data matters for our applications. And there are various interesting applications of sequential data, such as, for example, market basket analysis. Here we have a supermarket which collects the purchases of its customers, puts them into a database, and then they apply mining to discover interesting knowledge patterns, such as, for example, that people often buy beer and diapers together. This is an example, a popular example in the past from the data mining literature. Also, we can have web data where we record the web pages that people visit over time. And companies such as IBM, for example, are interested in discovering the sequence of web pages that people follow frequently to improve their website's layout, to see what products attract more interest, etc. Similar examples come from assisted daily living, where here we have smart homes and people who perform different activities inside their house. They are monitored for health purposes, and their data becomes a stream, a large sequence of events, which show their activities. And again, with mining, we want to discover interesting patterns or anomalies. For example, when an old person has an accident at their smart home. So we can see that sequential data is important and that mining is a type of analysis which attracts interest from business. However, it may also expose sensitive patterns. These patterns model confidential business knowledge, things that businesses deem as confidential, as private, and also these sensitive patterns may describe or characterize subpopulations of individuals, like, for example, people who have a certain buying pattern. An example comes from a supermarket, Target, in the US, which performed mining, and the patterns show that if a person buys certain products, then they are about to deliver a baby, they are pregnant. They use this sort of intelligence and to advertise products for pregnant women. And they sent a mail to a lady who was just 16 years old. When her father found about the mail, he complained to the supermarket saying that you advertise products for pregnant women to an underage girl. And then he had to apologize because actually the girl was pregnant. The data mining worked well, predicted the pregnancy before the father knew. So we can see that this, in that case, would be an example of a sensitive pattern. The exposure of sensitive pattern needs to be prevented because it can cause financial and reputational losses to organizations, like companies which have confidential patterns that are disclosed by mining, or it can lead to unsolicited advertisement to people which are described by the patterns, such as the pregnant girl I mentioned. Let's make now the setting a little bit more concrete. Here is an example of a sequential dataset. Each record corresponds to a customer and denotes the series of products that are bought from a supermarket, Big Mart here, over time. The time is not included, we just care about the sequentiality here. So for example, the first person bought product A, and then B, and then 2 times C, D, E, etc. Bigmart wants to improve their business intelligence, and they collaborate with market research company. So market research applies data mining, and they find the 2 types of patterns. One is that the sales for B, which is the own branded wine of Bigmart, are higher than F, where F is the own branded wine of Finemart, which is the competitor of Bigmart. So by mining the data, they find this pattern. They also find that the pattern D, F appears very frequently in the data. This means that a lot of people buy D, which is another wine, and then go on to buy F. If market research discloses this knowledge to Finemart, then Finemart can offer a discount for D, which will increase the sales of F, because D and F are bought together with this order. And then, of course, Bigmart will start losing business, because F and B are own branded wines by different companies which are complementary. So people buy either B or F. This is an example, a toy example, which shows the importance of protecting sensitive patterns. And this toy example is inspired by real examples in the business, where businesses really collaborated, and the disclosure of sensitive patterns harmed the collaboration. There are examples in the retail banking domain, and also in domains relevant to supermarkets and retailing companies. So here we deal with the problem of knowledge hiding or sanitization. It's an area in the general larger area of privacy-preserving data mining, which tries to prevent the exposure of sensitive patterns through the mining of data. Here, I'd like to emphasize that we talk about publishing a dataset. We are not interested in simply sharing the mining results, like statistics or association rules. We want to publish the dataset. So our goal is different from secure multi-party computation or output perturbation techniques, whose goal is to protect the result of the analysis. Also, our goal is different from anonymization. And for anonymization, there are a lot of nice principles like differential privacy, k-anonymity, and newer ones. The goal of anonymization is generally to prevent the identification of individuals or their sensitive information. But here we care about hiding specific knowledge. This knowledge may not correspond to individuals at all. It can be, for example, business processes or general statistics. Actually, this is the area of knowledge hiding is quite old. It started in the late 90s, early 2000s, with the work of Chris Clifton and Mike Catalach. And actually, in a paper of Clifton, they said that knowledge hiding can be complementary to statistical disclosure control, because it does an extra step to protect populations, not just individuals. So with anonymization, we protect individuals, and then if there is something that is sensitive and refers to subpopulations, we can apply knowledge hiding. There is, of course, a long tradition of works, and Vasilis Verikios has done recently an excellent survey. And if you read the survey, you'll find out that all of the methods that were developed apply to data that are non-sequential. We care about the sets, for example, and not order sets. And then we can delete events, we can add noise, we can do different things to protect unordered data, like association rules or frequent item sets. In our work, we consider sequential data. We were the first to do this back in the 2011, and there are actually more methods on that later, which are based on event deletion. Also, we considered last year event sequences, and there are currently no other works for event sequences. In this talk, I'll present two of our works. The first is permutation-based sequential pattern hiding. It is about collections of records, where each record has a sequence of events, like the products that I showed before. And it appeared in ICDM 2013, and it's a joint work with Robert from EPFL and Aris from IBM Research. And later in the talk, I'll briefly present our work on event sequence sanitization, which was published in SIAM SDM last year, and is done together with Robert from EPFL. So let's talk about permutation-based sequential pattern hiding. Here we have Big Mart, our supermarket, and Big Mart wants to share this sequential dataset to market research. The market research is interested in two types of mining: finding frequent sequential patterns like FGB, which are products that are bought in this order many times by many customers. They are also interested to do what's called a frequent item set mining, which simply means we want to find products that are purchased many times, but in any order, like GBD, here I denote it with a set, which means GBD or DGB or any other permutation is fine for us, it contributes to the counting, and we want to find the patterns that are purchased by a lot of customers. We have actually a threshold for the minimum support or minimum frequency, the minimum number of customers that want to buy these products. And we have sensitive patterns, which are sequential in our case, like ACE. So basically, Big Mart says that I don't want the pattern ACE to be discovered by mining. So a little bit more specifically, I want to share a dataset while limiting the support or frequency of these sensitive patterns by a chosen threshold delta, so that they are no longer actionable. By actionable, I mean that they do not help the competitors of Big Mart to do business. Their count is low, if you want. And while I do this, I want to enable the mining of other patterns by market research. So I want to minimize side effects, which are changes in the set of frequent non-sensitive patterns. Intuitively, I don't want to destroy the usefulness of data for any other mining task. And also, I want to minimize distortion. For example, I want to allow any other analysis apart from mining on the data. Like, for example, I can solve this problem very easily by deleting all the sensitive patterns from the data. But then the distortion would be high and the result would be useless for other analysis. So we have two utility goals here, and I'll make this problem more specific later on. Here is what the existing approaches do. They perform a deletion, and they apply some heuristics to do deletion in a good way. For example, they try to delete the minimum number of symbols that are enough to hide the sensitive patterns, or they aim to heuristically minimize the side effects. But we think that deletion is a drastic operation because it removes symbols from the dataset, it reduces their support, and for sequential data this is not necessary. Here is what it can happen if we apply the state-of-the-art algorithm SBSH with a threshold of 3. We have a pattern ACE, and we delete one occurrence of A to hide the pattern. So the pattern ACE appears 2 times, which is less than the threshold, and is no longer mineable. So the existing method protects the data, but at the same time, we cannot mine all these patterns. Like AC appeared 3 times, so it could be mined, it could be discovered by mining, but now after deletion it appears 2 times. So we cannot discover it and we lose useful knowledge. And this happens with all these other patterns. And if we are interested in frequent item set mining, where the order of events do not matter, we lose really a lot. We lose 25% of all the item sets of items that are frequent in this toy example. So we can see here that using deletion is drastic and is unnecessary. It destroys the data utility. So our proposal is to use permutation instead, which means that we swap the order of events in a sensitive pattern. Of course, we don't reduce the frequency by swapping because all the events still appear in the data, and because we don't destroy the order, our data is as useful as the original data for frequent item set mining and other tasks, mining tasks that are based on just the occurrence of events in records. But there are two challenges to apply permutation in practice. One is, what permutations are good for us? There are many different permutations. The number is factorial, of course, for a given sensitive pattern, factorial in the length of the pattern. So there are many, many permutations, and which are good for us, which can be used to avoid the side effects and incur minimum distortion, and also, provided that we have found these permutations, how will we use them on the large dataset that we have? For this, we need an algorithm. We need an algorithm to select the good records to which we will apply the permutations, and also we need a way to match the permutations to the occurrences of sensitive patterns. And this will be the largest part of our work. How we can generate permutations and how we can use an algorithm to sanitize the transactions. By transactions here, I mean the records of the data. Before introducing the approach, let me tell you a little bit what we consider a permutation and how we denote it. A permutation is simply a swapping of symbols of the sensitive patterns, or more formally, a one-to-one mapping from a set of positions in the sensitive pattern to itself. And we use the cycle notation to denote a permutation. We use it because it matches well with our distortion measure that I'll present later. And here is an example. We have a sensitive pattern S and its identity permutation. So basically this means 0, 1, 2. This means that all the events of the sensitive pattern appear in their original order. We don't permute anything. Now we permute and we get the permutation 1, 2, 0. So this means that where the 0th event appeared, now the first event appears. Also 2 is replaced by 1, 1 is replaced by 2, and 2 is replaced by 0. So we do a circular swap, if you like, and this is denoted with this cycle, which shows that 1 took the place of 0, 2 took the place of 1, and 0 took the place of 2. So we read it like that, and more generally, the cycle is simply a permutation that maps x1 to x2, 2 to 3, etc. The cycle notation is important, as I said, because we measure distortion by the Cayley distance, a measure which helps us to see how good is our data for general analysis tasks. And the idea is that if the Cayley distance is small, we have a permutation that is better for us. In terms of distortion, the Cayley distance is measured from the identity permutation and is basically a difference between the length of the pattern n and the number of cycles. So here is an example. We have the permutation 1 to 0. It has one cycle, as I showed before, and its length is 3, so it has 3 symbols. So the Cayley distance from the identity permutation is 2. And now we have another permutation, 0 to 1. It has 2 cycles. You see the first cycle is 0 because 0 didn't change its place from its original order. And then 1 and 2 swapped places. See, 2 got the place of 1. So we have 2 cycles, and the length is again 3, and the Cayley distance is 1. So we observe that the Cayley distance is smaller here, and this is a better permutation for us in terms of distortion, because it is the result of a single swap, while this is the result of more swaps. So this is the first usefulness criterion that we use in our approach. But we care about mining, so we want to preserve the set of sequential patterns that are non-sensitive. And how we do this? We want to make sure that when we swap the events of the sensitive pattern, we don't make the frequent patterns to become infrequent, so that they are lost from the mining, and we prevent the appearance of ghost patterns, patterns that were infrequent, unimportant if you like for the mining, and now become frequent, so they become important, and they are spurious patterns, they are fake patterns. So we want to generate permutations that do not result in lost patterns and do not result in ghost patterns. And here is an example. We have AC in the original data, we replace it with CA, so we permute the symbols, and then CA is lost. AC is lost, why? Because AC now became CA after the permutation. So the frequency gets lower And if it gets lower by a large margin, then it won't be discovered by mining. And here CB again, CB is ghost because this was BC, and after permutation it became CB, so it gains occurrence and then it will become frequent. So here we have a simple optimization problem that says, given a set of candidate patterns, I want to generate a permutation that avoids the side effects. This problem, as we proved, is NP-complete, and it gives us some indication of how difficult computational is our problem. Also, we want an algorithm to generate permutations that avoid the side effects with respect to the candidates and also have minimum distortion with respect to Cayley distance. And I'll present such an algorithm. There are some side issues like what happens if I cannot generate such a permutation. For this, we have heuristics in our paper. And there is another issue which says what happens if all the permutations do not make sense. For example, let's imagine that a customer buys an insurance product and then he cancels it. The only available permutation for me is to say that somebody cancels the product before he purchases it, just to swap these two symbols. But this doesn't make sense. So this is a forbidden permutation, and we want to avoid the generation of these permutations because they can be reverse engineered. And we do this in the paper. It's a simple extension in our algorithm, but I won't present it. Now I'll show you how we identify the candidate patterns for lost and ghost. Let's imagine that we have a sensitive pattern S, and we have a pattern which shares a subsequence with this sensitive pattern. So ABC is our sensitive pattern, S prime is our non-sensitive pattern, and these two share the subsequence AC. They also appear in the same record T. If I do a permutation which changes the ordering of symbols in this common subsequence, then the S prime will lose occurrence. So we can see here that if I change AC to CA, then before I had ADC, which is S prime, but now I don't have it anymore, I have CDA. And similarly, if one non-sensitive pattern shares symbols this time with a sensitive pattern, and I do a permutation, I may create the non-sensitive pattern so that it gains occurrence. And if I do this in many transactions, then I can have a frequent pattern which becomes infrequent, so it is a lost. Or, on the other hand, if I keep creating occurrences of a non-sensitive pattern by increasing its frequency, then I can have a pattern which was infrequent and now become frequent. So it is a ghost. And we have conditions with respect to supporting the paper. So we have identified our candidate patterns, and we need to generate a permutation that does not create ghost patterns and does not create lost patterns. This is called the pattern constraint permutation. But the good question is how we will generate this permutation. Nobody gives us the pattern constraint permutation. We need to build it slowly. And for that, we have the notion of partial permutation, which is a prefix of positions in a pattern. We have a prefix, and in our algorithm, we extend this prefix. And here is how we do it. First, we need to make sure that our prefix can be extended so that it gives a pattern constraint permutation. And we have conditions on that based on Cayley distance. So basically, if somebody gives us a prefix, we want to see if there are enough available swaps in the pattern that will lead us to the good permutation. And now, if this happens, we need a way to actually build this permutation. And for that, we have the algorithm, which is a randomized algorithm that simply performs a search on the space of different permutations. We start with the smallest prefix, which is just 0, and then we ask ourselves, how can we generate a permutation of two symbols? The next symbol, 1, can either come as a new cycle, so we don't permute actually these symbols, or it can be inserted in this cycle, so we permute 0 with 1. These are the two ways. And if this generates pattern constraint permutations, then we stop. If not, then we continue. So we iteratively build longer and longer prefixes, and our algorithm chooses permutations from the type of permutation that is more likely to produce a satisfying permutation. It is a simple algorithm which is linear in the number of candidates. This is good for efficiency, but it's cubic in the length of the sensitive pattern. This is not so bad because the sensitive pattern, remember, needs to be frequent. So it cannot be, for most databases, at least in the retailing domain, very large. So even the cube of that is something small. The length of the pattern is no more than 6 or 7 in practice, and what determines the complexity is actually M. And now we have our algorithm, which has 3 phases. First, it identifies the candidate patterns for lost and ghost. Then it selects transactions or records that are good to sanitize. And then it applies our permutation generation algorithm. We simply select transactions that, if sanitized, would be very bad for utility, and we keep them aside. So our algorithm selects transactions that are good to sanitize with respect to the upper bound of the side effects. So our theory for identifying candidate patterns allows us to choose transactions that are easy to sanitize so that we can maintain the utility of the data for mining. And here is how we use our permutation generation algorithm. We have a selected transaction, we have there the transaction sensitive pattern, and then we go over each sensitive pattern. Given a sensitive pattern, I have found the candidates. I use the permutation generation algorithm to generate a permutation that saves all the candidates. If I can do this based on the algorithm, then I just use this permutation and go to the next sensitive pattern. If not, in the case that there does not exist a pattern constraint permutation, I use the heuristic that I mentioned. So the idea is that I try to reduce the number of side effects when I cannot avoid them. And in some pathological cases where I only have one sensitive event, I cannot use permutation at all. So I resort to a simple deletion. And this is an algorithm, it's called PH for permutation-based hiding. It is an algorithm that is linear in the size of dataset, which is good, and it is linear in the number of candidates and the length of the candidates. So as we will see in practice, it is quite fast. Here are some experiments. We have applied our PH algorithm on 3 sequential datasets. These are all publicly available datasets. This contains about 1 million records and their web pages. This contains about 6,000 records, 60,000 records, and it's from the marketing domain. And this is a smaller dataset which has a large alphabet of symbols, which records the movement of trucks in a city. So we have got data from different domains, and we compare to the state-of-the-art algorithm, the SBSH algorithm that I used in the example in the beginning of the talk, in terms of data utility and efficiency. And here is what we found. We found that our algorithm has about 30% fewer side effects than the competitor. This means that the data we produce are much more useful for sequence pattern mining compared to the data generated by the competitor. Also, the ghost patterns are not really a concern because they are very few and only when the sensitive patterns are large. Also, we verified that deletion is a drastic operation because the competitor lost up to 20% of the frequent item sets. So the data for frequent item set mining was very bad, while in our case we simply used permutation, so the data was as useful as the original data for frequent item set mining. We also measured KL divergence between distributions of data and which are important for building general mining models, and again our algorithm was up to 30 times better than the competitor. This means that the counts of the events did not change by permutation, and also the counts of frequent item sets did not change. In terms of efficiency, our algorithm is slower than the competitor by 4 times on average, But this doesn't matter so much because even in the large data set, the algorithm didn't take more than 100 seconds. So both algorithms are scalable. And at this point, I'd like to stop with the permutation-based work and continue with the event sequence knowledge hiding work. So here, with the event sequences, we can see that our data changed. We have a sequence of time-annotated events. For example, Big Mart now aggregates the customer data in the form of a stream and saves it to market research. T1 can be Monday. We know that one time that the product A was purchased one time. The product B was purchased 4 times, etc. Then T2, the next day, different products were purchased, like D 7 times, and then this continues and continues for long, and this gives us a stream of events. We want to apply frequent event mining here to find out events whose relative frequency exceeds a threshold in any different prefix of the sequence. So here we deal with a stream of events, and we apply mining in different prefixes that start always from the beginning of the stream. Our sensitive events should not be exposed, and here is an example of a sensitive event. The event A had relative frequency 1 out of 10 here. We can see 1 out of the sum 5, 4 plus 1, 10. So it was infrequent here. We were okay. Then we continue, we get this prefix, again okay. If we get these 3 time points together, then the relative frequency of A exceeds the threshold, and since it is a sensitive event, we need to protect it. And how we protect it? We apply event deletion. What is the challenge here? The challenge is that we have a lot of ways to delete occurrences of a sensitive event from a large number of time points. You can see that the number of ways is exponential, and actually it maps to the number of weak compositions in mathematics. In practice, n and m are in the order of 1,000 here, so we have a really huge space of potential deletions. And of course, if we start deleting events, we will lose data utility, and we need a clever way to delete events so that we maintain the usefulness of data for mining. The problem is, of course, that there are strong dependencies between events in the entire sequence. For example, if I delete one event, let's say A, from this time point, I change the relative frequency of all events here and here and here in every part of the sequence that contains this time point. And how do I change it? The relative frequency of A will get smaller because I deleted something, but the relative frequency of all the others would get larger. So we see that we need actually a utility model to control the usefulness of the data after deletion. And we propose such a utility model. I will go briefly over it. And since we have our utility model, we formulate an optimization problem to change the data, apply deletion to the data in an optimal way according to the utility model. I will show you how we define the problem and the algorithms that we develop for solving the problem. So our utility model, very briefly, is based on the distance between probability distributions. Here we have a sequence of events and a segment of the sequence, one time point of the sequence. And A is our sensitive event, and we deleted the only occurrence of A, so A is 0. Actually, A 0 is not part of the published data set. We just use 0 here for illustration purposes. What happens if I delete one occurrence of A? The relative frequency, or the probability, if you like, of A drops here. But the relative frequency of B and C, which are non-sensitive, increases. So we have one probability distribution for each event. And the deletion changes the probability distribution. So to measure utility, we quantify the difference between these two probability distributions. And we use the squared difference. And actually there is some issue with the zero frequency. What happens if I have only one event and I delete it, then the denominator would be 0. So we apply additive smoothing here to deal with this. And in the end, what we get is a model which is applied on the entire sequence and tells us how good is our deletion strategy for the entire sequence. So this is our simple utility model. And a good property, which is actually why we use the squared distance, is that we want to penalize drastic changes. Like, for example, many people were buying A, but now I deleted everything and I tell the person that receives the data that nobody purchases A. This should be penalized because it changes the distribution abruptly. And our model achieves this. Now we have our model, so it's time to define our problem, which is called event sequence sanitization, or ESS. So we get an event sequence, we get a set of sensitive events, they are defined by the data owner, and we get a threshold delta. We seek to construct a sanitized event sequence by applying event deletion so that first, no sensitive event can be mined from the data, so no sensitive event remains frequent in any prefix of the sequence, and also the utility of our event sequence is optimal according to our model. We have studied the problem and we found that it is weakly NP-hard. So the term weakly here means that there is hope for designing a pseudo-polynomial optimal algorithm. And actually we designed such an algorithm, which is called Odessa. This is applied to cases where we have only one sensitive event. Let's see the heart of Odessa, how it works. It is based on a dynamic programming equation. It actually finds the error of deleting a given number of occurrences of the sensitive event from a certain prefix of the sequence. And to find the best way, the best error, the minimum error, it considers all the possible ways in which we can delete the given number of occurrences from the prefix. So here is the example. Let's say I have an event sequence with one time point, and A is my sensitive event, it appears one time, and I tell you delete the single occurrence of A. How many ways I have to do this? Just one. I simply delete it. Now I have two time points together, and I tell you please delete one occurrence of A. How I can do it? I can either delete the occurrence from this time point or from that. And what happens if I have two occurrences? I need to distribute them into these time points in all the possible ways. And now imagine that this is a very large sequence with thousands of time points. You can see that I need a principled way to quantify the error. And this is what happens with the dynamic programming equation, which basically distributes the number of deletions between the last time point of the sequence and the remaining prefix. Now, we use this dynamic programming equation in the algorithm. How we use it? First, we solve a system of linear equations to find out the minimum number of occurrences that we need to delete so that the sensitive event is not frequent, to protect the sensitive event. Then we apply the dynamic programming equation iteratively in all prefixes of the sequence. And we fill a single dynamic programming array, and this gives us the error. For example, this cell 4.2 gives us the error of deleting 4 occurrences of the sensitive event from a prefix that contains 3 time points, 0, 1, and 2. And if we do this in the end, and with some backtracking, we get an optimal way of sanitizing the event sequence. The algorithm is optimal, as we prove in the paper, with respect to our utility model. But this doesn't mean a lot in practice, because in practice we care to see if the result is still good for mining. And in our experiments, we saw that the result is good for mining, and to convince you, I have plotted the distribution of 3 non-sensitive events in this slide. We can see here that the probability distribution of the event B after deletion, which is the dotted line, is close to the original distribution of the event. And the same happens for C and D and all the other thousands events. So we can see that the impact of deletion is not much. And this is good for building mining models because they are based on the probability distribution of events. Also, our algorithm is linear with respect to the number of events and time points, but of course it is pseudo-polynomial. I said it before. It is pseudo-polynomial, which means that it has a numerical parameter inside the complexity, and if this numerical parameter gets very large, the algorithm will get slower. Actually, since the problem is weakly NP-hard, we cannot avoid this behavior. But of course, we can build heuristics which are faster. Now, let me show you how we deal with the case when the event sequence has multiple sensitive events. This is actually simple, simpler than we thought, because it suffices to apply our Odessa algorithm to each sensitive event iteratively. And this retains the optimality of the solution. So we have our algorithm ESA, which simply applies the Odessa algorithm iteratively to each sensitive event, and we have evaluated the algorithm using different datasets. The first is called ADL, and it models the activities of daily life of people in a smart home. This is again publicly available dataset. The second dataset we use is called ENTRE, and we denote it with ENT here, and it is from a web-based recommendation system where people recommended restaurants in the Chicago area. And also we use synthetic datasets generated by the IBM synthetic data generation of up to 2 million events and 100,000 time points. And here is what we have found. We have found, firstly, that the number of deleted events, the percentage, is very low in practice. Even though we have 200 events or 500 events, and we are stringent in terms of our protection requirements, the percentage of deleted events is relatively low. It was never more than 0.25%. So we don't do a lot of deletion if we use our optimal algorithm. Also, we found that we do not generate fake events, ghost events. And here is the example that shows it. Even though we have 500 sensitive events in the most difficult dataset to sanitize, we never had more than 8.2% of ghost events. In the other datasets, this percentage was much lower. And in practice, the number of sensitive events is small. And also, we wanted to measure the efficiency of our algorithm and the runtime, how it scales. And we found that it actually scales sublinearly with the dataset size, which is with the number of events in the sequence. And it takes a few seconds, less than 2.5 seconds, even for event sequences with 1 million events. And again, the dynamic programming doesn't take a lot of memory. The memory was less than 30 megabytes, which shows that designing optimal algorithms using this dynamic programming framework is good, of course, for effectiveness, but does not really sacrifice efficiency. So to conclude this talk, I introduced the problem of sanitizing sequential data, and I presented two flavors of the problem. The first was for a sequential dataset, and our approach used permutation. The base of the approach was that permutation created a better result in terms of usefulness compared to deletion. Then I moved on to the problem of sanitizing an event sequence, and I presented a deletion-based approach, which, as we showed, performed very well in terms of effectiveness and efficiency. Thank you very much for your attention.
Okay, thank you very much indeed. That's great. Very clear, very nice slides and so on. According to my email, I haven't had questions, but it does seem, according to Robin, nitro's been again a problem
Right.
seeing the stream. So that's unfortunate. But anyway, perhaps I could start by asking about these. You talked about sensitive patterns, and you sort of have a kind of threshold. You were, I think, explicit about it here, particularly. I just wondered how you go about choosing a threshold. I suppose as a statistician, one might even think about, whether there's a sort of significant evidence of sensitive pattern, but I guess that's not being done here. I think you had a sort of a certain percentage that you defined.
Yes, this is a very good question, and I'll tell you how we do it in practice. So in practice, the business that has the data performs the mining first to find frequent patterns. Then the business experts see the frequent patterns and select which sensitive pattern, which patterns make sense of them, and they are confidential.
Yeah.
So this is done in practice with a very low level of support. So you can say, for example, 0.5%. So they get really lots of patterns, and they say, okay, these 3 patterns for us are confidential, so let's give them to this algorithm, which is applied after the mining, and we hide them. So our algorithm gets it as a parameter, and in practice it requires pre-processing by doing data mining with a low support threshold. Actually, it would be very good if somebody had a measure to tell what is sensitive. But this is difficult because here we talk about business data and it's quite subjective. So one supermarket, for example, may make a lot of money from a pattern whose frequency is quite low, and the competitors didn't think about it. So that's the sort of quick answer.
Okay.
Yeah, I guess my question was a bit similar, really. So you have to specify the sensitive patterns that you want to protect. But I assume that market research goes and mines for all sorts of other patterns. So it seems to me that there is a potential there for some of those subsequent patterns, you know, to then actually become sensitive because they've been found by the external organisation. So I wondered what sort of, you know, by then it's too late, I guess, because you've already found them. I wondered if you had any comments on that sort of feedback loop or how that works in practice.
Actually, the feedback we had from the experts was that we know the patterns that we make money from. So we know the patterns that helps our business. We mined them before, and now we give the data out.
So why do they give the data out?
They give the data out for 2 purposes. One is to satisfy legislation, data sharing agreements and stuff. Like, for example, in the bank domain, there are agreements where they motivate, if you like, the financial institutions to give out their data for monitoring purposes.
And they don't mind that it's sanitized?
They can apply other algorithms for preventing individual identification or others, but this sort of technology is just to hide confidential patterns that bring financial benefit. And another setting.
Yeah, you said that another reason, yeah.
And another setting which is also of importance is when the businesses collaborate. So, for example, a supermarket collaborates with a retailer to improve their supply chain operations. This requires different analysis, but the business who owns the data wants to be protected in case that they do mining and they find the things that bring, you know, they are not relevant to the supply chain operations, but they are relevant to business intelligence.
Yeah.
Yes, this is an open problem actually. If somebody comes with a good measure to find what is sensitive, then it would give a general maybe and a more perhaps statistically founded way for us to give the input to our algorithm.
Yeah, surely it's context dependent as you discussed. Yeah, interesting.
Yeah, you wonder whether, I don't know, with some data mining is exploratory to reveal patterns that perhaps the first company hadn't seen, but
Yes.
I guess you're saying that they're fully aware of the what is going to be the most sensitive in relation to their business, and that's
So the market research company figures that out, but they've got it wrong because the real answer is hidden.
And
Consequences.
sometimes there is also a trade-off here, in the sense that they want to gain some benefit from the market research, but at the same time they want to hide something. So if they hide everything, like for example, the simplest thing for us and for the algorithm is to set the threshold to 0. So this means I completely delete all the sensitive occurrences of the patterns. And then nobody can mine them, nobody can find these events at all. This is very simple. But then the
That's right, it gets suspicious.
the big mart will say, okay, I will lose a lot of interesting patterns which overlap with the sensitive ones. So that's why let's set the threshold a little bit higher. So I guess there is also a trade-off between protection and usefulness here.
All right, well, thank you very much.
Thank you.
Thank you once
Thank
again.
you.
Right.